Hello everyone and welcome to this live support event with GRASS Sound and Vibration, an Axiometrics Solutions brand. My name is Teresa Rubio, and in today's webinar I would like to introduce you to Ole Thalgaard, VP of Support and Applications at GRASS. Welcome Ole.
Thank you.
Before we begin, I want to cover a few housekeeping items. At the moment you are all muted. We will start first by answering all the questions that some of you submitted during the registration process. There are many interesting ones, I have to say. But for those who didn't, you can submit them now through the questions section on your screen. We will try to answer these questions afterwards. However, if we run out of time or a longer explanation is required, Ole will follow up after the event via email. Lastly, I would like to remind you that this online event is being recorded, and in a couple of days you will be able to watch it again, as we will send an email with the link to watch it on demand. So without further ado, Ole, I would like to start reading the questions. So are you ready?
I'm ready. I'm always ready.
That's good to hear. So, first question. I am using a 46 AE half-inch microphone on a regular basis. I'm interested to know the noise floor data in a third octave bands for 46 AE half-inch microphones.
Okay. It is actually available. The data here are actually available on our website for the different microphones. So it is actually available for all our microphones and also in 1/3 of an octave band. The table, if you would like to have the data in table format, then you have to contact us and then we will send it out to you. These in the table is not available from our website, but of course we have the data. So you can always contact us and we will send you the data for the noise.
Good. Then the next question is, especially interested in microphones for DAC measurements and microphones for aeroacoustic wind tunnel testing. And then in connection with this, we also have, I'm wondering how big of a radius distance we should consider to get the total number of diffuser air drill that we should consider when performing the AIHRI HAVAC calculation of the noise generated at the diffuser air drill.
Okay, let's have a look at these two questions. I think actually we will start with the first question and then we will continue with the second question. But these two questions have both something to do with aeroacoustics and actually measurement in flow. So I think actually it could be a good idea to have a little look at measurements in flow. I also have to tell all of you that this is actually a very, very big subject, and we will not be able to cover everything during today's live event. It's something where we can use hours to explain. So we will I will try to do it very short. When measuring airflow in Dutch system, noise, the noise in the Dutch system can be determined by air velocity, the velocity of the air, and the size of the Dutch. Let's have a little look in general of measurements in flow. See, when we're doing measurement outside in a nice day as we have here in Denmark today, then we have some wind, and it could actually be wind with a flow speed of 1 meter per second to about maybe up to 50 meters per second. We can do inside measurement in ventilation systems, measurements on fans, and things like that. We can also do measurements in wind tunnels, where we have a more controlled wind speed, and directions where we might be able to measure from 1 meter per second and up to high Mach levels. When we are looking at these, doing these measurements, then there are actually two parameters we in general actually are talking about, and it's aerodynamics and aeroacoustics. Let's have a little look at what is actually the difference between the aerodynamics and the aeroacoustics. Aerodynamics, it is actually a flow measurement. It is a static pressure measurement. Normally, we are talking about high sound pressure levels, and we are talking relative low frequencies. If we look at aeroacoustics, then again, it's a flow measurement we're doing. It's not a static pressure measurement, but it's a dynamic pressure measurement. So here we actually have one of the difference between aerodynamics and aeroacoustics. It's normally a turbulent field we have, so we will have a lot of turbulence. We are looking for sound sources. Normally it's relative lower sound pressure levels and higher frequencies we are looking for. Aeroacoustics, if we look at the aeroacoustics, then we can talk about hydrodynamic pressure fluctuations, and we can also talk about measurements in the boundary layer. If we have a flow, as we have, let me see if I can. I cannot point, but we on the first drawing. Oh, thank you.
You're welcome.
Thank you. We have a flow, and we have the signal, turbulent signal, and this turbulent signal will, of course, be picked up by our flush-mounted microphone. If we look at the frequencies for the microphone, then it's actually equal to the velocity of the flow divided by lambda. If we look at the same at an acoustic pressure fluctuation, then we are actually looking for sound sources. So the frequency is in this case equal with the velocity of the sound divided by lambda. What is a measurement microphone measuring? The measurement microphone is actually measuring the pressure difference between the inside of the microphone and the outside of the microphone. Like we have it here on the little drawing. We have the pressure outside, actually the pressure on the diaphragm. Then we have the pressure inside the microphone, and the output of the microphone is actually the difference between these two pressures, the pressure inside and outside the microphone. If we look in a dot and how the flow in a dot system is. It could actually look like this. In the middle of the dot system, we will have what we call a laminar flow. in the top of the dot system, there will be some turbulence because the flow will be the speed of the flow will be reduced due to the walls in the top and in the bottom and the size of the dot. So if I place a microphone like I have done here in the blue dot on my slide here, then I will measure, it could be a sound pressure level in 1/3 octave as indicated here on the picture. If I do, and this is a measurement out of flow where we only are doing an acoustical pressure measurement. If I measure here in the top where we can see there's a lot of turbulence, then we can see that we are measuring much higher, and it's actually due to this turbulence. So we are actually making in the turbulent transitions acoustical pressure and the turbulent pressure, and therefore the level is actually very high. If we measure in the middle, where we are measuring in the laminar flow, let's see, we will measure a little bit less than we actually did in before. And here we will again measure the flow, the acoustical pressure, and the turbulence we actually have in the flow in the middle, actually in the laminar flow. If we measure in the bottom on the black dot here, then again we will measure a relative high sound pressure level, and again it's turbulence. It is in the boundary layer. So we have an acoustical pressure and the turbulence. So for measurement in flow, if we would like to do directly in flow where we are measuring in the laminar flow, then we are talking about free field measurements. First of all, we need to use a free field microphone. And let's see what's happening when we are using this free field microphone. We have here the dot system, laminar flow in the dot system. When we place the microphone inside this system, then the microphone, due to its own size, actually will generate some turbulence. So it will actually disturb the flow, and we will actually measure wrong values or higher values than maybe than expected. So we actually have to do something with the microphone for doing correct measurements in this laminar flow. So what are we actually going to do? We have to minimize the microphone's influence in the flow, and it can actually be done by a windscreen or a nose cone for these measurements. Windscreen we can add here, and if we look at the graph, then we can actually see the influence of a windscreen when we add a windscreen. If we have no windscreen, then we are measuring around 100 dB. If we add the windscreen, then we are measuring around 80 dB in this neighborhood. We can also add a nose cone, which will also reduce the turbulent noise and make the microphone not disturbing the feel or the flow the same way. We can also do what we call pressure measurements, where we are measuring in the boundary layer, in the wall of the dot system, in a wall of a wind tunnel, measuring in the boundary layer. For this, we can use different types of microphones. For all of these microphones is that it's a microphone, either it's a flush microphone or a flush surface mounted microphone, a flush mounted microphone, a flush mounted microphone with a turbulent screen, so we can remove some of the turbulence we might have in the boundary layer. Let's have a look at surface mounted microphone. Surface microphone is used where we have wind introduced noise measurements. Outdoor measurement on testing grounds can it also be used for wind tunnel measurements. Surface mounted microphone are mounted without damaging the structure. We are not drilling a hole for the microphone inside on the door, for instance, of a very nice new car, but we are mounting the microphone on the surface of the test object or the surface of the wall in a wind tunnel. Glass do have a huge range of surface microphones. We have the 40LA and 40LS. This is actually microphones based on a quarter-inch standard quarter-inch microphone, but it's very, very thin. They only have a height of 2.5 millimeters. We do also have the new surface microphone, the what we call UTP microphones, the 40LA and 40LX. These microphones has only a height of 1 millimeter. Okay. And it's not much. And it means that these microphones will have no impact or a very, very, very little impact in the field. So they will not generate additional noise or additional turbulence to your measurements and therefore measure wrong signals. Flush mounted microphones is actually microphones we are mounting in our test object. If we are testing on a car, and then we drill a hole in the door of the car and mount our microphone in that hole. So the microphone diaphragm is flush with the rest of the door. So we will have a very, very low profile in the door. So a flush mounted microphone will have no influence on your measurement. Yeah, all the different microphones, they can actually be used for surface mounted principle, but yeah, we have to make a hole in the structure. In some cases, we are interested in the acoustical noise generated by a noise source, and therefore we will like to get rid of the turbulence we have in the boundary layer. For doing this, we can actually use a microphone with a turbulent screen. And let's see how this is working. If we have a microphone, a very small microphone, it could be a 1/8 of an inch microphone, and we flush mount this microphone. And then the signal going over the diaphragm and measured by the diaphragm will be rather small, because normally microphone will average over the diaphragm. If we have a bigger microphone, it could be a half-inch microphone, and then the signal now will be average over this half-inch microphone, so the signal we are measuring will be even smaller. If we use a turbulent screen, where we actually have a big screen, which we could call a first diaphragm, and then a little bit below that screen we have the microphone itself we are using for the measurement. So we actually have the big screen, and we will average over this big screen, so we will actually get rid of the turbulent noise, but we will still be able to see and hear the acoustical noise. So this is a way to reduce the turbulent noise from our measurements. Like we see it here, we will actually be able to dampen the turbulent noise with up to 25 dB. And then the second question, yes. This is a question for air conditioning systems. So let's have a look at that one. It is actually a question where we are working according to a standard, the AHRI standard. And if we look into this standard, then it's actually written there, for being able to fulfill this standard, then we actually have to do sound intensity measurements on our what is it called? Aircon systems, yes, sorry. And these has to be performed according to ISO 1914-1 or 1914-2. It is actually so that both of these standards, they are actually pointing at another standard, the standard for sound intensity measurements, the IEC 61043. So let's have a little look on sound intensity for understanding this. Sound intensity is defined as a power carrier by sound waves per unit area in a direction to that area. Sound intensity is measured in watt per square meters. For doing sound intensity measurements, we need to have an sound intensity probe. And sound intensity probe consists of two measurement microphones. These two measurement microphones, they are paired together, so the microphone has the same sensitivity, and they have a very, very, very well-defined phase match. And then the next thing, when we have sound intensity, then we have a little spacer. If you look at the picture, there's a black ring, and this black ring is actually a spacer with a certain distance. And depending on the frequency range you are measuring in, then this spacer can be longer or shorter. The principle is in sound intensity is that we have these two microphones, and these two microphones will actually measure the time difference between the two microphones. And by knowing the time difference, we know this, the distance between the two microphones. The distance is actually due to the little spacer. Then we are able to do a calculation of the sound, like we have here on the pictures. So we are calculating the sound intensity, and for doing this and for doing these measurements, we will need a sound intensity probe. It could be a probe like the GRASS 50 GI RP. You will also need a suitable sound intensity analyzer. It must at least be a 2-channel analyzer, again with a good phase match, and of course a program for doing the calculations of sound intensity. And then we have to perform the measurements according to ISO 9614 or 9614-2. The 9614-1 is where we are measuring a couple of seconds in a grid. So we have to make a grid over our measurement object, and then we have to start in one corner and then use the probe in that corner for a couple of seconds, and then we have to go to next little square and next little square. If we do it according to the ISO 9614, then we have to make a scan, and it means we have to make a continuous movement in the same speed over the surface of our measurement object, and it has to take about 20 seconds, not less than 20 seconds to scan the whole surface. It is a near field measurement, so you actually have to be around 10 to 25 centimeters from the dot. Low frequency measurement.
That's the next one. Okay, so the next question says, why do I often have a lot of low frequency noise, less than 20 Hertz, when measuring noise, and how can I avoid it?
Oh, that's a very good question. And yeah, a lot of people doing measurements, they will actually see this from time to time. First of all, what can actually cause low frequency noise? Yeah, maybe you are doing measurements in a place where there is a certain amount of wind flow. Maybe you are doing the measurement outside, or you are doing it in a place where you have structure-borne sound noise. It could be some vibration coming from the basement or whatever, creating this low frequency noise. Or it could actually also have something to do with your venting of the microphone. Maybe you have forgotten that there's a little venting hole on your preamplifier of the microphone, and maybe you have plugged this venting hole. Let's have a look on how to avoid it. If the measurement is done in an environment with wind noise, is it actually recommended to use a windscreen? The windscreen will damp some of the low frequency noise, like we can see here. So if we have a high turbulence damping up to 20 dB, up to 2 kilohertz, and low turbulence damping approximately 10 to 20 dB, up to 4 kilohertz, or in the frequencies range between 200 hertz to 4 kilohertz. It's one way. There's another way. If the measurement is done in an environment with general low frequency noise and structure-borne noise, is it actually recommended to use a high-pass filter to remove the low-frequency component? Many analyzers, many of the GRAS power modules, they do have a high-pass filter, a 20 Hertz high-pass filter, so you will actually remove all the low-frequency components you might have in your measurement. Another thing is actually the venting. Have you plugged the venting hole? See, we have the venting. We have venting. Actually, we have two venting systems. We have rear venting microphones where we have a little hole in the back of the microphone. It's very difficult to find and see, but there is actually a little hole. And then there's a smaller hole in the preamplifier, and this and via this hole the microphone is actually venting. We also have some microphones called front-vented microphones. These microphones are mainly used in the previous questions we had where we were talking about aero acoustic measurements, when we are doing measurements in flow and in wind tunnel, where we might have a pressure difference between the front of the microphone and the back of the microphone. It is very important that we don't plug the venting hole. See, I have a little example here. If we have a microphone and we have plugged this venting hole, if we move this microphone up and down in 1 meter, then it's actually the same, or 1 meter static pressure difference is the same as 0.033 millibar. If we calculate that into Pascal, then it's equal to 3.3 Pascal. And if we calculate that into a dB level, then it's actually equal to 104 dB. So if I plug the venting and I move up and down my microphone with 1 meter, then it's actually equal to, I have created a sound pressure level of 104 dB. So of course it will create some problems when I'm doing my measurements. So the conclusion is that don't cover the venting hole, and don't cover the venting hole with labels, stickers, holders, whatever we could cover it with. We do actually have an application note describing this little issue, and it can be found on our website. So my recommendation is, first of all, ensure that you haven't blocked the venting system. Use windscreen for damping the low frequency noise. Will also avoid eventual overload saturation of the microphone capsules, which might have an influence at higher frequencies. So if you try to damp at lower frequencies, then if you overload the microphone at low frequencies, then maybe you can't see it, but you might have some resonance tones at higher frequencies, which make your measurements a little bit strange and weird. And use a 20 Hertz high pass filter like this.
The next question is, what are the best practices when using ultra low noise microphones like the GRAS 40HF?
Yeah. First of all, maybe a low noise microphone is a microphone with a very high sensitivity. These microphones can actually measure very low signals, actually below threshold of hearing or below 0 dB. The GRAS, as mentioned in the questions, the GRAS 40HF is a 1-inch low noise microphone, and is actually able to measure down to -2 dBA. Handling of a low noise microphone. See, a low noise microphone is a little bit more sensitive than a standard measurement microphone. So a low noise microphone must be handled with care. It means you should avoid drops, shocks, dumps, and it should not be used in a very dusty environment. Drops, shocks, and dumps, things like this, it will actually, every time you knock the microphone into your table or floor or whatever, then the microphone, it might work after, but some of the mechanical parameters or mechanical parts, they will be not misaligned. And if you misalign it, then the microphone will change its sensitivity, and it will also change its frequency response. If it's changed its sensitivity, then maybe you can't measure the low levels as you would like to do with the low noise microphone. So therefore, you must handle it with care, and more care than you handle a standard measurement microphone. Like a standard measurement microphone, when you are working with it, then you have to do a calibration, or I would actually call it daily verification. The daily verification can be done by a standard calibrator, but for a low noise microphone, you cannot use it at higher levels than 94 dB. If you use it at higher levels, then you will overload the microphone. And again, if you overload a microphone, then the microphone will start clipping, and you will actually stress the diaphragm of the microphone, which after long time used or exposed for these high levels, then the microphone will also start drifting. When measuring, then you should actually use the same consideration when you are measuring with a standard microphone. And also some of the consideration we talked about before with low noise, with low frequency components in your measurements. So in general, with low noise microphone, be a little bit more careful, else use it as a standard measurement microphone.
Good. So next question. Does mechanical and acoustical vibration affect microphone performance measurements and accuracy? And if so, how can this be separated from the acoustic signature? Are there submersible microphones for immersion cooling? Many questions.
Many questions. We will start with the first with the first question. Yes, mechanical vibration will have an impact on your measurement. It could be airborne or mechanical noise. It could be structure-borne, where it is a vibration noise. With airborne noise, I'm actually meaning that you have your microphone is mounted somewhere, and you have next to that something which is vibrating a lot. So you're actually measuring the noise from this object vibrating a lot. If it's structure-borne, then maybe your microphone has been mounted on a part which is generating a lot of noise. So this noise will actually vibrate the microphone as well. A microphone can actually be described as a single degrees of freedom vibration system, also called the spring mass model, where we have M, the mass, and for a microphone it is actually the mass of the diaphragm. We have the stiffness, or S, the stiffness. S is actually the stiffness and the tension of the diaphragm, and then we have the system damping within the microphone. Normally is made via the back plate we have in the microphone. So we could actually make a drawing of a microphone, single degrees drawing of our microphone, like we actually have here, with a mass, the mass of the diaphragm, the stiffness is the stiffness of the diaphragm, and the damping, which is mainly controlled by the back plate of the microphone. If we look at this, then there can be some called transverse vibration, and it means if we move the microphone, if my pen is the microphone and we move the microphone in this direction, so it will not have any effect when we are doing the vibration on the diaphragm itself. The microphone has actually a very, very low sensitivity for transverse vibration. We could also talk about axial vibration. Axial vibration is when the microphone is mounted on an object which is moving up and down. So it will actually have an effect on the diaphragm of the microphone. Moving up and down. The effect is relatively low due to the low mass of the diaphragm, and it is actually insignificant below resonance frequency. At resonance frequency for the microphone, then it would be relative high, and then it will damp again above resonance frequency. In our specifications for a microphone, the influence for axial vibration is actually specified. Typically, it is in the neighborhood of 60 to 70 dB SPL for 1 meter at 1 meter per second square vibration signal. Then the question was how to find out what is the effect and how to separate the vibration part of what the microphone is picking up with the acoustical part for what the microphone is picking up. And yeah, in general, it is actually difficult. But a method for doing that is if it is possible, not impossible, but possible to measure the vibration level in the position where you have mounted the microphone, then it's a good idea to do that. And when you have done that, then use what we have given you in the specification for the microphone, how many dB SPL will you actually have for 1 meter per second square vibration signal. When you know that, then you can calculate with the actual vibration signal you actually have, and then you will actually find what is the level you are generating by the vibrating signal. And then with the microphone, you will measure the acoustical noise plus the noise coming from the vibrating object, and then you can actually subtract these two from each other. In general, if the acoustical noise is 10 dB higher than the vibration noise, then your error will be in the neighborhood of 0.5 dB, as mentioned here on the graph. So this is something you can calculate if you know the vibration level, then you can actually calculate how much it actually will be in acoustical dBs. We do also, for this part, have a technical note, which also can be found on our website.
And next one is, are there submersible microphones for immersion cooling?
And yeah, the answer, see, actually all our microphones, they are actually specified in a temperature range. Most of them, they work from 30 down to minus 30 degrees. We do also have some microphones which have been tested and working down to minus 55 degrees Celsius. So actually most of the microphones, they can actually be used as long as you are within the specifications we have here for the microphone. One thing we have to remember when we are using microphones and we have different temperatures is that the microphone is actually temperature dependent or has a little temperature dependency. So we have what we call a temperature coefficient for microphone, and typically the temperature coefficient is in the neighborhood of 0.01 dB per degrees Celsius. So if your temperature range is going from minus 30 to, let's say, 100 degrees, then the change in sensitivity of the microphone will change by 1.3 dB over this temperature range. I do hope this answers your questions. I think it was the question.
Yes. So now we have actually approximately 10 minutes left for any other additional questions. These were the ones we received during the registration. So as mentioned at the beginning of the event, you can use your Q&A section to submit now any other questions you may have, and we will answer that. While we give it a couple of minutes, we will take the chance now to tell you that if you would like to join to our next live event support, you can already save the date, November 6th. And if you want to know any other upcoming webinars and events that we are running the next couple of weeks and months, you're more than welcome to visit our GRASS event section, where you have access to all the information. So let's see. Since there's no questions yet.
They will come. They will come.
But it was very, very interesting, many of them. And I hope that our audience also found them very interesting.
Yeah, and please have in mind, if you would like us to go a little bit deeper into your questions, then you are very, very welcome to send us the questions again on support@grassacoustics.com, and then we will answer much, much deeper than it was possible here on this event today.
Yep. Well, I will then also mention that this webinar has been recorded. So in a couple of days, you will receive a follow-up email, including the link to watch this event on demand. So you will be able to watch it again. And as Ole mentioned, if you want to dive deeper into any of the topics that we discuss here, or you would like to, answer any other technical questions to Ole and the support team, you are more than welcome to do so. So yeah, I think then that should be for today. Thank you, Ole, for your explanations. Thank you to our audience, and have a good rest of the day, or good day if you're on the Americas. And we look forward to see you again in our next webinar.
Yeah, on the 6th of November. See you there.
See you. Bye-bye.
Bye-bye.